Okay, moving on to lesson 2. So this is where this unit gets quite a bit more confusing. So in this unit, we introduce a second way to measure angles. So far we've always measured angles in degrees. Now we're measuring angles in radians. So what it means to measure angle in radians is we're really figuring out how many radiuses go along the circle to get to our angle. So if this is my angle measure in radians is figuring out how many radiuses fit right here. Now, we did a bit of an exploration in class and we made our little crafts that help us with radians. So we're not going to do the exploration in here. We're going to go to the next page. So we're going to quick talk about converting between degrees and radians. So since an angle can be measured in degrees or radians, it is important to be able to convert from one measure to the other. For a lot of us, it's much easier whenever we're given radians to convert it and work in degrees. You don't have to, and it's good if you try and work in radians, but there's nothing wrong with converting back and forth. The only exception where you can't do that is if we need something in exact value of radians. It's a little bit trickier to do that by converting back or forth. So consider a circle with a radius r units. Complete the following. So one complete rotation in degrees is 360 degrees. The arc length for one complete rotation is 2 pi r. So when it talks about arc length of one complete rotation, that's really just the circumference of this circle is 2 pi r. So the ratio arc length to radius is really 2 pi. So this means if we're measuring our whole way along around the circle, r could fit around the circle 2 pi times. Remember, pi is just a number, and it's 3.14. So 2 times pi is a number around 6, a little bit higher than 6. So what this is telling us is if we had a string and we could pick up this radius, we could fit it around the outside of our circle a little bit more than 6 times. Because 2 pi doesn't sound like a number, but really it's a little bit more than 6. So what does this tell us? This tells us that 360 degrees is equal to 2 pi radians. Okay, well, what about half a rotation? So one rotation in degrees is 180. Well, what is the arc length with 1/2 rotation? Well, if the full rotation was 2 pi r, half of the circumference would be pi r. The ratio would be pi r over r, which is pi. So this tells us how many times would a radius fit around half a circle? Pi times. So 3.14 continues on. That's how many times, that's how many radiuses we would need to get around half the circle. So 180 degrees is equal to pi radians. So pi radians is 180 degrees. So how do we find what 1 radian is? Well, we divide both sides by pi. So 1 radian is 180 over pi degrees. So to convert from radians to degrees, you multiply by 180 over pi. From 180 degrees is pi radians, so 1 degree is pi over 180 radians. So to convert from degrees to radians, you multiply by pi over 180. So in mathematics, the symbol with this little open circle following a number means the unit of angular measure is degrees. If there is no unit after the number, or there is the abbreviation RAD, or the word radians, then the unit is in radians. For example, if you wish to write the sine ratio for a right angle, you must write sine of 90 degrees, not sine 90. Sometimes radians will be written as an exact value, and then they'll have pi in it. So you might have an angle like 2 pi over 3. It's pretty obvious it's in radians. Sometimes, though, you could type in Remember, pi is just a number, so on your calculator you can go 2 times pi divided by 3, 2 pi over 3, and that gives us the value 2.09. So sometimes they'll write that angle as 2.09, and then it's less obvious it's in radians because we don't see the pi in there. But both are describing the same angle. So this is very important to remember. Pi radians is 180 degrees. If you are converting from degrees to radians, you multiply by pi over 180. So I always remember that. We're going 2 radians. We have the pi on top. Radians to degrees, you multiply by 180 over pi. So example 1, convert from degrees to radians. Give your answer as an exact value in terms of pi. So we're converting 2 radians. So we're going to multiply by pi over 180 degrees. The easiest way to do this, if you in your calculator type in 270 divided by 180 and ask it to give it to you as a fraction, it's going to give you 3 over 2, and then you can stick the pi in there. So this is 3 pi over 2. 315 degrees, so again, we can multiply by pi over 180. So if your calculator, you put 315 over 180 and reduce it, and then put the pi back in. So 315 over 180 gives you the fraction 7 over 4. So this is 7 pi over 4. If you were asked to give this as an approximate value to the nearest tenth, that's what we're going to do in the next one, then you just type that pi into your calculator. So convert from degrees to radians to the nearest tenth. So again, we're going to multiply by pi over 180. Well, now on my calculator, I'm just going to type in 70 times pi divided by 180, and it's just going to give me a decimal approximation, 1.2 radians. So sometimes we leave it as an exact value and we don't type in the pi. Other times you can just punch in pi and you'll have your decimal approximation. Same thing here, we're going to go 205 times pi over 180. This is going to give us 3.6. Okay, now we're going the other way. Convert from radians to degrees. So now we got to multiply by 180 over pi. Well, this is nice because the pi's cancel out. So we really just have to go 180 divided by 4, which is 45 degrees. And of course we can have negative angles just like we had with degrees. So I'm going to multiply by 180 over pi. Pi's cancel out. So negative 7 over 3 times 180 gives us the angle negative 420. And if it's given in decimal form, same thing. We're just going to round to the nearest tenth. We're going to times by 180 over pi. Just type the whole thing in your calculator. 1.57 times 180 over pi gives you 90 degrees. Negative 1.4 times by 180 degrees over pi. And this gives us negative 80.2. Okay, continuing on here. Coterminal angles and reference angles in radians. So everything we did with lesson 1, we have to do again with radians. So coterminal angles are angles with the same terminal arm. They are separated by a multiple of 360 degrees or 2 pi radians. So remember with radians, 2 pi is 1 full rotation, just like 360 degrees. The principal angle of a set of coterminal angles is the smallest positive rotation angle with the same terminal arm. The principal angle is between 0 and 360, or between 0 and 2 pi. A reference angle is the acute angle formed between the terminal arm of the rotation angle and the x-axis. The relationship between the rotation angle and reference angle in each quadrant is given in the table below. So, same thing from that other lesson, from last lesson we looked at. In quadrant 1, your rotational angle just equals your reference angle. No matter what units we're in, that's going to be true. An angle in quadrant 2, the rotational angle is equal to 180 degrees minus the reference angle. Well, in radians, we're going to go pi minus the reference angle. In quadrant 3, the rotational angle is 180 plus reference angle. If we're working in radians, it's going to be pi plus the reference angle. 4, 360 degrees minus the reference angle. So in radians, just going to be 2 pi minus the reference angle. So in each of the following, draw the angle in standard position, determine the principal angle, determine one positive and one negative coterminal angle, write an expression involving the principal angle that represents all angles that are possible. Okay, so first, 3 pi over 4. So one way to remember this is always 0. This is pi over 2. This is pi. This is 3 pi over 2, and then a full rotation is 2 pi. So 3 pi over 4, we have to look at 3/4 away around this, 3/4 of the way around half the circle. So where's 3/4 of the way around half the circle? Right here. Another way to think of it is, if we think of equivalent fractions, this would be 2 pi over 4, this would be 4 pi over 4, so 3 pi over 4 must be halfway in between there. So that's where it should be. Second question was, state the principal angle. Well, the principal angle is just the angle between 0 and 2 pi, so that's the one it gave us. 3, determine one positive and one negative coterminal angle. Well, to find a positive coterminal angle, we can just add 2 pi to it. Well, how do you do this? Well, if you're using your calculator to add the fractions, you can just type in 3 over 4 plus 2 and stick the pi back in afterwards. So 3 over 4 plus 2 is 11 over 4. So this must be 11 pi over 4. To get the negative coterminal angle, we're going to subtract 2. So same thing, type in 3 over 4 minus 2. You get negative 5 over 4 and put the pi back in. Part 4, write an expression to show all of them. Well, when we were working in degrees, we'd say plus 360 n. Here we're going to say plus 2 pi n, where n is an integer. So same thing, except we're just working in radians. Negative pi over 3. Well, this tells us we're going to go 1/3 of the way around half the circle. Remember, pi is half the circle, so 1/3 of the way around half the circle. But we need to go clockwise, so that's going to put us here. This is the angle negative pi over 3. So, next part of the question, what is the principal angle? Well, that means we want to go this way. Now, remember that to get a full rotation would be 2 pi, which would be the same as 6 pi over 3, just working with equivalent fractions. So we're not quite at 6 pi over 3, we're 1/3 short of that. So this angle must be 5 pi over 3. Positive and negative coterminal angles, so we're just going to add 2 pi and subtract 2 pi. So here in my calculator I would type in negative 1/3 plus 2 and then put the pi back in. So this gives me 5 pi over 3, which happens to be the same thing as our principal angle here. Minus 2 pi would be negative 7 pi over 3. And to just give a general expression, I would have negative pi over 3 plus 2 pi n, where n is an integer. Whoops, not where n is pi, where n is an integer. Okay, last example of this part. Determine the reference angle for the following rotational angles. 4 pi over 3. Okay, so remember, if I'm working in threes, this is 0. This would be 3 pi over 3. This would be 6 pi over 3. So 4 pi over 3 must be in here. We've come here, we had 3 pi over 3. We have to go 1 pi over 3 further to get 4 pi over 3. The reference angle then, we can go 4 pi over 3 minus pi, or 4 pi over 3 minus 1, and that gives us our reference angle of pi over 3. Negative 5 pi over 4. So if I'm talking negatives, this is 0. This is negative 4 pi over 4. This is negative 8 pi over 4. So where is negative 5 pi over 4? So we come here to negative 4 pi over 4. We need to go pi over 4 further. So we get here. What is the reference angle? Well, we could say negative pi, subtract a negative 5 pi over 4, gives us our reference angle of pi over 4. 23 pi over 6. Well, where is 23 pi over 6? So now we have to do some full rotations. It's easiest if we first change this to be between 0 and 2 pi. So we can actually subtract off 2 pi here. And this gives us 11 pi over 6. Well, if I'm working in pi over 6s, so that means I'm splitting half the circle into 6 pieces. So this would be 0. This would be 6 pi over 6. Back here would be 12 pi over 6. That means my angle 11 pi over 6 is in here. If this is 11 pi over 6 and a full rotation is 12 pi over 6, the reference angle must be pi over 6. You will notice that with these, it's fairly obvious what your reference angle is. If you have a denominator of 3, your reference angle is pi over 3. If you have a denominator of 4, your reference angle is pi over 4. If you have a denominator of 6, your reference angle is pi over 6. Now this holds for these special angles, which are the ones that are in our special triangles and the ones we're expected to use with exact values. Okay, the last part of this lesson, this is a long one, arc length. In this lesson we define radian measure of an angle theta as the length of the arc forming the angle, or the arc length, divided by the radius. This is a formula that is on your formula sheet. It is written like this on your formula sheet. We can rearrange the formula so theta equals a over r in terms of arc length as a equals r theta, but that's not the way they have it on your formula sheet. They have it this way. The most important thing about this formula is that angle is in radians. That part is not specified on your formula sheet, so you need to remember that in this formula, theta has to be in radians or the relationship doesn't hold. So a is the length of the arc around the angle, and r is the length of the radius. Almost every time they ask a question on the diploma exam to calculate the arc length, they're going to give you the angle in degrees. So you first need to change that angle to radians, and then you're ready to use this formula. So, example 7, a pendulum 30 centimeters long swings through an arc of 45 centimeters. Through what angle does the pendulum swing? Answer in degrees and in radians to the nearest tenth. So we have this pendulum that's 30 centimeters long, and it swings through an angle that we're trying to solve, but we know that the arc length, so this distance, is 45 centimeters. So we are looking for the angle. We know that we have a radius of 30, and we have, other way around. We have an arc length of 45 and a radius of 30. So when we do this division, we get 1.5. Now, this is in radians. So to convert it to degrees, I'm going to multiply by 180 over pi. It just wants to the nearest tenth. So when I divide by 180 over pi, multiply by 180 over pi, I get 85.9 degrees. Example 8. Calculate the arc length to the nearest tenth of a meter of a sector of a circle with a diameter 9.2 if their sector angle is 150. So now I'm asked to calculate the arc length. I have a diameter of 9.2, which means I have a radius of 4.6. They always like trying to trick you with any questions to do with a circle by giving you that diameter instead of the radius. And I know this angle is 150. So this is the type of question on the diploma exam. They usually supply the picture for you, but we need to realize that we need to change this to radians before we can go to the formula. So again, if you want to work in exact values, you type in 150 over 180, change it to a fraction, you get 5/6. And this is 5 pi over 6. So our angle is 5 pi over 6. The arc length is what we're looking for over the radius of 4.6. So we're going to type in 5 pi over 6 times 4.6, and we're going to get an arc length of 12.0. And it's going to be in the same units that our radius was in, so meters. Last example, a circle with center C and minor arc AB measuring 15.2 centimeters is shown. So when they say minor arc, they mean the shorter distance between A and B. The longer distance around the circle would be called the major arc. If angle ABC is equal to angle BAC, which equals pi over 6 radians, find the length of the radius of the circle. So it says that angle ABC, so that's here, equals angle BAC, which is here, and it is pi over 6. So the first thing we need to do is figure out this angle, because that is the angle that we need to calculate the radius, to use our formula for arc length relating radius to the angle. Well, we know that a triangle adds up to 180 degrees. We know in radians 180 degrees is equal to pi. So I'm going to take pi, I'm going to subtract off my two angles of pi over 6, and I'm going to find out that that center angle is 2 pi over 3. If it is easier for you, you can change these things to degrees. So pi over 6 radians, that's 30 degrees. 180 minus 30 is going to give us our central angle, and you can change it back to radians to use in the formula. That's up to you. So now I'm going to use my equation. I have 2 pi over 3 equals our arc length, which is 15.2, times the radius. So to solve for r here, I'm going to have to take 15.2 divided by 2 pi over 3. And that's going to give me a radius of 7.3